know-how to create building materials. Like Rama said, normally we're extracting, and we're trying to find different ways to do that, because as we know, embodied carbon is a big deal, and if we can figure out how to reduce embodied carbon in the built environment, we can really make some significant headway in the fight against the effects of climate change. We're a pretty small team, but we're a diverse team. We're designers, architects, engineers, and builders. 3 of the 4 founders are here today, myself, Dr. Kabanda, and Chris Magwood, and they'll introduce themselves briefly in their sections. Our 4th co-founder, April McGill, she's working on a great hempcrete project in her hometown of Charleston, South Carolina, and so she's not able to join us today. But we've been at this for 5 years, and it's been an exciting ride. But the truth is that mycelium-based composites have been around since about the early aughts. A gentleman by the name of Phil Ross, he was an artist at Stanford, doing a lot of work. He was also an amateur mycologist, and just noticed that the blocks that he was using were something to use as an art medium. So up in the upper left there, you can see a small structure he had built with some bricks, and was just kind of just having fun with it, and then realized
Josh,
that there was. Yes,
sorry to
ma'am.
interrupt you. You're not sharing your screen. So when you said the
Oh,
upper
gotcha.
left, there's nothing on the screen.
Oh, gotcha. Oh, it's not okay. Let me stop and reshare real
Sorry
quick.
to interrupt you speaking, but I was like, wait, he's referring to a visual.
There we
Perfect.
go. How about that? There we go. Okay, great. So upper left, that upper left. It was kind of interesting, and as also an amateur mycologist and somebody who's spent a lifetime just obsessed with fungi in the forest, I knew of this art. I lived in the Bay Area for 28 years. Currently in Chicago, actually, we're at a great incubator space here in Chicago. But around 2013 or so, you started to see the first companies creating products with this, as mentioned, styrofoam replacements for packaging. Some really neat projects were done to make bricks and make structures, but the structural component was not made for the mycelium-based composites. I had only heard about mycelium-based composites when I was at a design workshop with a friend of mine, Kobe Barty, and he's an architect, and we were talking about materials at this design workshop, and how terrible they are. It's just, as a designer, you want to make beautiful things, but we have that thing, oh, that's to die for. And I mean, literally, these materials are killing us, and we got to make sure that we do better. And so when I heard about this, I said, oh, great. Well, I feel like I want to be the first designer to make a chair out of these mycelium-based composites. And he goes, no. You don't understand. They're not that strong. You can't do that. Well, I love a good challenge. So I took that back home and thought, okay, I'm going to do this. But what I quickly realized is that, gosh, there were actually dozens of chairs that I found on the internet that were in the shape of chairs that were made with mycelium-based composites, or you saw people just growing mycelium on top of an existing chair. But I noticed something. Nobody was ever sitting in them. So I was like, oh, Kobe maybe was right. So I took that as a challenge. Still, I love a good challenge. So I did some more research and found out that when you look at the literature at that point, 5 years ago, there were only maybe 30 or 40 papers written on the subject. What they always ended with was, yes, but they can't really serve in structural capacities, but can serve as like sound mitigation panels, like the ones you see in the bottom right there from a company in Italy called Mogu, or as insulation or styrofoam packaging, or these pure mycelium products that are like leather replacement. Phil Ross's company, Wrks, has a really great leather replacement called reishi that's currently making really big waves in the materials world here. But as I mentioned, I'm really obsessed as a designer. I'm obsessed with chair design, and on the left there, that was my final project when I was at Academy of Art, made with concrete and steel. Two of the most highest embodied carbon materials that we've got. Just like one of those things that led me to believe, well, we could do better. So as I mentioned, I took that challenge on and made a mistake, actually. And as you can see there, I kind of was just trying to be creative with how to use this leftover material when I made my first forays into making these materials. I made a mistake in the lab, and that mistake had dramatically different properties than the research that I was reading. And it really got me thinking that perhaps just making a chair really is kind of like setting the bar way too low. And knowing the problem of embodied carbon, I thought maybe there's a better way to use this material. But that didn't stop me from still wanting to explore, could I make a chair shell that was really strong and that could actually hold up the human body? And so we took the method that I was using early on and put together these disparate parts. And then, as you can see, they started to fuse together in a process that is now known as myco-welding. And it was fascinating. And in just 5 days of growth, you see that all of these parts adhered together. And then I even put a piece of jute along the back there, and it completely laminated that piece of jute to the back there. And I thought, hey, I really, really, really think we're onto something. And as you can see in the picture of me standing on that, I mean, it's on the fulcrum there, and I'm really trying my hardest to break that. And what's really interesting about fungi is that you know, people think of fungi as kind of this monolithic kingdom. We say, hey, we're going to use fungi to do X. But the thing is that the fungal kingdom is an incredibly diverse set of organisms, all the way from yeasts and molds and single cell fungi up to the higher order fungi, as they're known, the polypores. Those are the ones that you see growing on the sides of trees. The ones that I'm actually obsessed with. I have thousands of photos of fungi from over the years. And it just comes to find out that the ones that I have a love affair with are a part of this really small subset of fungi that express the 3 different possible morphologies of filamentous fungi. So not all fungi create these filaments that create a mycelium. And as I mentioned, the mushrooms or the fruiting bodies that you see in the forest, those are not the organism. Well, it is a part of the organism, but it's the reproductive part of the organism. The organism is actually the mycelium. And from the naked eye, they all look the same, just kind of like this slathering of white, fluffy material kind of floating through areas. And all filamentous fungi create generative hyphae, and that's what you see up here in the upper right. The generative hyphae's job is to rapidly explore an area and find food. Animals engulf their food, plants can photosynthesize, but fungi have to absorb their food. And so their process of moving through a substratum helps them find food that they can consume, but they have to exude their enzymes. And since they have to absorb their food, surface area becomes the name of the game. So being able to rapidly explore is one of the interesting, unique aspects of fungal biology that we can tap into. A small subset of fungi also create a second type of hyphomorphology called skeletal hyphae. So quick terminology, there's the mycelium, which is the whole colony, and then the individual strands of that colony are called hyphae. And I'll go over these 3 types here. So there's the generative hyphae that explore, and the skeletal hyphae, again, only in a small subset of organisms, create these 2 types. And then an even smaller subset of fungi create a 3rd type called binding hyphae. And the skeletal and binding hyphae do exactly like they sound like. The skeletal hyphae provide a little bit more structure, and the binding hyphae glue all of those strands together so that they can protect their food source and live for very long periods of time. As long as there's a food source available, a fungus can continually live. You may have heard about the organism, the Armillaria, that's in Oregon, that's been growing for thousands of years and is several hectares in diameter, and it's an incredible organism. But we can tap into this very small subset of biological capabilities to create basically a matrix phase for a composite material. Our patented technology is unique because what we do is we get rid of the rigid mold, and we basically fabric form our parts, but also are able to interleave in sections of internal textiles that are a reinforcement phase for the material. And that reinforcement is what really lends itself to creating the strength of our material. And it also allows that organism, fungi are like you and me. They share a lot of characteristics with humans, and we share more evolutionary traits with fungi than we do with any other of the kingdoms there. So that's quite neat. But they breathe oxygen and breathe off CO2. Now they can live in high CO2 environments, but that's their preference. And our method eliminates the rigid mold, which creates a buildup of CO2 and kind of depresses their growth. And our process allows them to fully respirate. And I think that's my hypothesis, is that's what lends itself to creating these structurally capable materials. I mentioned that myco-welding process. And so we started to look at what could we do in the built environment to make an impact with this material. And so we started to look at harnessing that capability to weld these parts together. And so we made some early prototypes of what can become a SIP wall. And so you see on the left there, those were wet just out of the chamber, but you see they're all stuck together. And then after drying, there it is, a very strong structure. They're basically integral to each other. We sent that off to an independent lab, and they wanted to pull the parts together for some strange reason to test them. And they had to take a bandsaw to actually shave off the ends there. And I'm not sure if you can see me, but we're actually now able to make these thinner panels now. And so we're hoping that our next iterations of these, that are first of all going to be bigger, and then we can actually make them thinner. And that's also quite exciting. One of our advisors, Dr. Andrew Dent, who is at Material Connection, he's a really great material scientist, and he was blown away when I first met him and showed him our materials. And it's been really encouraging, because it's really neat when you stumble upon something and then are able to work with some really great individuals to bring something further. And again, we're still pretty early on, even though we've been at it for 5 years. The pathway that we're taking is quite different from what most folks want to do with mycelium-based composites. The low-hanging fruit is styrofoam replacements or pure mycelium products. And actually, it's a small community, and all of the rest of the community kind of advised me in the beginning, don't building materials, it just takes too long. And I thought to myself, if nobody does it, it will never happen. So we've been just doggedly, almost stubbornly moving forward with trying to create structural building materials with it. And so far, we've gotten some great traction, and we've just entered into a multi-year research collaboration with the Argonne National Laboratory. That's why we've moved our R&D efforts here to Chicago, so we could be closer to the lab. That research will be starting up pretty soon in the summertime. And then we have a really great corporate partner in AXA XL, and they've hired us to do some demonstrations of basically mycelium-based composites in general for their new flagship office in New York City. In the back there, you can see that's a big feature wall that's in the main lobby, and those pixels there, we call it the pixel wall. Those are all mycelium-based composites and a 3D knit fabric structure that those are all grown on top of. It's 10 feet tall, 12 feet wide. The moss wall side was done by others, but that's our first in the wild application. We're also creating some architectural elements and some chairs for other parts of this office as well, and we'll be delivering those this year as well. Let's go over some of the science behind this. And it's really quite interesting. Like I mentioned, back 5 years ago, there was only 30 or 40 papers. Nowadays, there's probably more 300-400 papers written on it. It's really picked up steam. But the early research is interesting. And one of the top researchers in the field is Dr. Elise Elsacker. As far as I know, she was one of the first PhD students to do a PhD on mycelium-based composites. And this was a quote from her dissertation, where she's talking about the fact that this is sort of the first time in history where we've taken a material and not done really the fundamental science on it, but really skipped ahead and tried to make products right away. And I think that sort of was one of the reasons why the applications have been less, not structural, because there hasn't been enough research into the fundamentals of the biology. I spent 18 years in public health, as a clinician before I went into design. And so I had a background in human biology, so it wasn't a big leap for me to learn a lot about the fungal biology, and it was quite interesting. And it's tapping into that know-how about the lifestyle of fungi that created, I think, the wherewithal to get to where we are right now. Mitchell Jones is a researcher that's done a lot of the really great work on really learning about the fundamentals of the qualities of the material. Found out that the fungal mycelium-based composites are really good at sound attenuation. They're also pretty decent at thermal mitigation, or thermal resistance. And what's interesting is you can see there's density along the bottom, thermal conductivity here. And you can see that the density here is about 100 kilograms per cubic meter. And our material is about a little over twice that, but we still are clocking in around the same thermal conductivity numbers there. So that's interesting to think, because as you know, the axiom goes, the more dense of material should get, the least thermal resistance it might have, and we're not finding that actually. So that's something that we need to explore further. We certainly haven't done extensive testing on this, and that's what we're doing in these next few years with Argonne and our partners here. One of the things that plagues mycelium-based composites is this water uptake. It is a problem. When fungi are in the wild living, they're amphipathic, meaning that they can be both hydrophobic and hydrophilic. And in that, oh gosh, I'm seeing a low battery there. I hope I don't run out of batteries here. The research shows that they can accumulate almost 200% water uptake. And our anecdotal data, we haven't done extensive testing on that. We're looking at more like 20–30% as opposed to 200%. It's also got some pretty good fire performance numbers here as well. Here's a little video that we did to just kind of show the difference. This is obviously just anecdotal, but you know, it shows, here's the previous formulations, really great for styrofoam replacements and packaging. However, as you can see, the material is easily broken. And here's one of our parts. I'm standing on it with both feet. I'm kind of jumping up and down on it, trying to break it. They just don't break. The wall of that structure there is about 25 millimeters or an inch thick. And so that's kind of exciting. Also for Mitchell Jones here, you can see that after 18 days, they're getting these nice thick hyphal mats there. But in just 5 days, this is a Sen image that we've had of our material that only needs 5 days of growth to achieve sort of the same qualities here. Here's some Sen images of our material. We're going to zoom in here on it, and you can see the larger strands there showing the interface of the cotton material and the fungal mycelium. And then also, here's the image at about 1200 times magnification showing the individual hyphal strands there. So you can see it's mostly space. There's a lot of air in there. And then here's a really close-up zoom of the bigger structure there is the cotton fiber, and then the smaller structures there are the fungal mycelium gluing everything together. And that's what's so incredibly interesting there. The CT scans we've done, I think this is the future of research here in material science, is using CT scans so we can look at these things intact. And what's very interesting is that we can segment out the different phases here. So we can remove the hemp hurd, for instance, and we can see that this is, from a material standpoint, we're making a composite material, but our matrix phase, instead of pushing the glue through the material, our glue grows from within the particles there. So that's how they're holding things together so strongly. And it's quite amazing to see these CT scans and to be able to analyze the material in this way. But not only are we able to qualify the growth, but we can also quantify the growth with CT scans. And that's also quite exciting. And I think this is going to help us push the knowledge of this further faster. And CT scans are also just kind of fun to look at too. These are some charts showing where the other composite materials land on the scale of stress strain curves. We're clocking in around 1 megapascal, which is not knocking any engineer's socks off, but it is sort of the basics to get into there to structural applications. And here's from Dr. Elsacker's dissertation showing a morphology that's, pretty mushy, not very rigid. And here's when we normalize our data over the top, you can see how ductile our material is. And that ductility is what lends itself to the strength. We're about 1.1 orders of magnitude stronger, and also 4 orders of magnitude stiffer than previous known formulations. But there's still some work to do. I mentioned Phil Ross in the beginning. He just announced the development of an organization called Fung, Fung. And what he's trying to do is help researchers that want to look into this. He's helping give them a leg up. Instead of starting from scratch and learning how to work with these materials, he's showing that he's trying to give researchers a toolkit to work with so they can go further faster. One of the really interesting quotes from a book that I love called The New Science of Strong Materials by J.E. Gordon. He says that if we're going to use biogenic materials, we've got to learn how to enhance their ability to stop fractures. The crack formation is the bane of material existence, especially in the built environment. And as you can see there, that's a time lapse of one of our compression tests there. And that center part of that material is still intact. In fact, that material is right behind me, and I can still stand on that cylinder, and it's largely intact in the middle, and it is still just as strong. So that's where the promise of this lies, and we're really excited to keep developing that. So I'm going to pass it off to my colleague and co-founder, Dr. Kabanda, who's going to talk a little bit about why nature's blueprint is going to help us create better structures. So take it away, John.
Thanks, Joshua, an amazing presentation. So as Joshua mentioned, my name is John Kabanda, and I'm a co-founder and VP of Engineering at Okom Labs. At Okom, we're looking to fungi to develop new building materials. And that's because currently we find ourselves limited to a small menu of building materials. So we have things like steel, concrete, and timber. However, using these materials is not the answer to decarbonize the building industry. And that's the main reason why we need new building materials for the building industry. And likely, we don't have to look far. Nature's blueprints offer innovative solutions that have evolved over millions of years, showing the efficiency and resilience of biological structures. Leveraging these blueprints and geometry, we can develop lightweight mycelium composite structures due to the following reasons. 1, efficiency in structure design. Natural structures like honeycombs, spider webs, and plant stems exhibit sophisticated geometric patterns that maximize strength while minimizing material use. So, mycelium-based composites can mimic these patterns, creating lightweight structures that efficiently distribute forces similar to how bonds and shells work in nature. 2, optimization for load distribution. Geometry-driven structures in nature are optimized for load distribution and damage resistance. By following these patterns, mycelium composites can be designed to handle specific loads efficiently while maintaining low weight, making them suitable for a variety of applications like lightweight construction. And finally, innovative functionality. Natural structures often exhibit multifunctionality, where geometric forms offer not just strength, but also insulation, fluid flow optimization, or enhanced surface area. So mycelium composites can incorporate these features, providing additional benefits like thermal regulation or improved acoustics. In summary, drawing from nature's geometric patterns and combining them with mycelium's unique properties enables the creation of lightweight, efficient, and versatile composite structures. This synergy opens new avenues for sustainable design, offering both functional and ecological advantages across different industries. Thank you. Did we lose Josh?
We may have lost Joshua and the slide deck, but hopefully he'll kick back in.
Yeah. I'm back. So sorry about that. I did lose power there, but I'm trying to get the slide deck back up. So sorry about that.
Hopefully everyone was able to follow what I was talking about without the slides.
All right. Well, I will just start with a quick introduction and hope the slides join us shortly. So my name is Chris Magwood, and I have about a 25-year career in design and construction, home design and construction. My focus has been on natural materials and low carbon and carbon storing materials. I've been an educator and an author, and I call myself an accidental embodied carbon expert. Really, you know, I came across the notion of carbon storage and embodied carbon through wanting to be able to quantify for our clients the kinds of advantages that our buildings were offering them. So, you know, we had long been using things like energy modeling tools, waste tracking systems, systems that track toxic materials in our buildings, and the notion of embodied carbon and carbon storage sort of followed from that. And it was very clear right from the start of those explorations that natural fiber materials, you know, have this incredible advantage in terms of how they have taken carbon from the atmosphere and stored it in the material itself, and where we can use those materials, especially without a lot of modifications or treatments. The result can be a building with a really large amount of net carbon storage. And sorry, it's a little distracting to have things kind of coming and going here. But essentially, you know, with natural fibers, there's a huge range of natural fibers available to us in the natural world. A lot of the ones that I've focused my attention on are agricultural residues, and my interest in those is that these are things that we're already producing as a you know, a co-product of our food production. So we have all kinds of straws, stalks, shells, stems, all of which have, you know, been used in buildings and building construction for thousands of years, a lot of which have shown up in sort of more modern forms. But essentially, because these things are all tend to be individual pieces, you know, whether it's an individual strand of fiber or a larger stalk, what you need to be able to build with them is some sort of glue that's going to hold them together. So we know we've got all these fibers that are abundant. The slide that's up now is a quote from Roads to Removal, which is the US government's look at carbon removal from the atmosphere, and basically, you know, pointing to the fact that biomass wastes are a huge potential source of carbon removal. You know, somewhere in the neighborhood of 700 to 1,000 million tons on an annual basis coming from our existing food systems. But we need some sort of glue to hold them together. And in the construction world to date, you know, we've bound fibers with, you know, string, twine, or wire. We've bound fibers with natural binders like clay or lime or even cement. We've bound fibers together with petrochemical glues. You know, there's been a whole range of ways to stick things together. We've used heat and pressure to do that, but all of these glues work, and all of them show up in the built environment, but all of them tend to have one or more major drawbacks, and that could be toxicity. It could be a reliance on fossil fuels. It could be the need for a lot of energy to create the heat and pressure to treat them. It could be that they are, you know, dissolve when they get wet. But, you know, they all kind of, you know, have strengths, but they also have weaknesses, and usually more than one weakness, which has sort of meant that biocomposites haven't really taken over the construction industry the way they could, because really we're waiting for the right glue to come along, to, especially for structural purposes, to make all of this abundance of fiber practical for construction. And so like Joshua said, about 4 or 5 years ago, I got in the mail this sample mycocomposite tube from Joshua. And, as soon as I opened it up and as soon as I touched it and as soon as like I sort of felt the strength of it, it was this aha moment, like, oh, mycelium is the glue. It sort of checks all the boxes that we need to be able to take these small pieces of fiber that are abundantly available and actually turn them into something that we can build with. And so, I mean, I really was quite literally very excited by that development, and immediately reached out to Josh and was like, how do I help with this? Because this feels like the kind of thing that could really revolutionize construction. Not only is the sort of glue, or the way that the mycelium sticks everything together, really kind of it just really does check all the boxes, but the material itself is formable. And so, the beauty of a material like concrete is that whatever shape you sort of put the material in, it hardens into that shape, and that formability is also something that the mycelium composites really have. And so, right away, I could see so many uses for this in the built environment, whether it's as, structural insulated panels, where the mycelium is both the structure and the insulation in the panel, interior wall partitions, ICF blocks, dividing partitions for interior walls, door slabs. I mean, the list of potential uses sort of went on and on in my head from the minute I touched this material. And so I think that the notion, Rama said it really well off the top, is that the sort of flip from relying on going and extracting raw materials to working with mycelium, where there is a raw material, but it's typically a byproduct or a waste material, but really kind of growing our materials and harnessing the sort of incredible work that mycelium do to kind of inhabit all of that space and create these really strong structures around this agricultural waste. To me, it's really exciting, and I'm really looking forward to helping Okom kind of take the great research into mycology and the growth that Joshua is doing, and John's incredible work on form and structure, and bringing my experience in the construction world to say, well, these are the kinds of products and the kinds of forms that this material could show up in that would be really useful to builders and designers to sort of move this material into wider use. So I'm really excited about what the future holds for Okom, and I think we're kind of at time for our presentation. So I'm really looking forward to taking whatever questions folks have.
And
Thank you
apologies for
so
the
much.
power issue there. Oh my gosh. Geez, I remember my first Zoom call. Yeah.
I'm gonna take advantage of the fact that I'm the host and ask the first question. Josh, at the very beginning, you said that you made a mistake in the lab, and that lab led to, the change in the way that you were thinking about it, but you actually didn't say what that mistake was. So
Yeah.
it might be intentional, but can you share what that mistake was that led to, changing the way that you were thinking about using fungi and mycelium for?
Yeah. So the common knowledge was that you do kind of what we always had known, and when you're making some kind of formable material, you put it into a rigid mold. And knowing something about the biology, it kind of dawned on me that perhaps that rigid mold was a little counterintuitive or counterproductive to the growth of the mycelium. And I mentioned that I was in pre-hospital medicine for 18 years, and fancy way of saying that I was a paramedic, but I spent most of my time in public health doing research. But my time in the field, I also did a lot of bike race standby. So I had this stockinette material that I had in my medic bag for those races, because it's a great way to hold bandages on legs and things like that. And I had, when I first did my first experiments, I didn't know how to measure it in order to make the first experiments. I was just going to do it just the way that everybody else did, doing good science. Let's recreate what was done before. And I had like a 5-gallon bucket left of material, and I didn't know what to do with it. And so I'm scrambling around. What do I do with this material? So I grabbed some stockinette and I just started shoving it inside to see what would happen. And I didn't even think about it. I put it up on the shelf and wasn't even worried about it. I didn't even like track its growth during that 5 days. And even when during the drying process, I was actually a little discouraged because all the parts that I was growing for my experimentation weren't what I thought they were going to be. I could break them all with my hands. They were really weak. And I was just thinking, oh boy, this is going to take me a long time. And I was sitting there, I made some, I don't have one with me here, but I made a little pencil holder too with some of it, with that stockinette material too. And I was holding that, kind of fidgeting with it, and I was wrapping my knuckles on it, looking at the shelf of all of the experimental parts that I had made, thinking, gosh, if I could just find a way to make it more rigid. And I realized the part that I was holding was making this tick, tick, ticking sound. And I said, wait a minute, let me go look at what is now affectionately known as the poop emoji. That was that coil that I showed you in the beginning there. We called it the poop emoji. And I pulled that down, and I'm realizing, oh my gosh, it is so vastly different from what was up on the shelf. And I put it on the ground, I'm standing on it, and I'm like, oh my gosh, this is really strong. It was weeks into the process that I realized that I had kind of veered into a different direction. And it took me another 9 months to really realize what the impact was and how I was achieving that through the biology. But that was basically it. It's really just a desperation trying to use leftover material.
Excellent. If anybody else has questions, I do have a second question, and it's not related to the work, but related to the company name, having heard Chris now say it out loud and realizing I've been saying it wrong. Is it related to Occam's razor, or?
You got it. Yeah.
Okay. Thank you. I was like, I was calling it Okom, and then I heard Chris and I was like, he definitely said Occam.
Yeah, exactly. Yeah. Occam's razor. And I spell it funny because I'm a designer, so that I have that latitude.
Fair enough. There's no umlaut. You're doing well.
We do have a question in the comments,
Oh, great.
John, and it is, what about the water uptake issue? Oh, wait, let me start from the beginning. You mentioned the research into structural thermo sound performance, but what about the water uptake issue, which would enable external use?
Mm-hmm. Yeah, it is definitely an issue. It's one of those things that through adding other types of biogenic materials, I think we can further increase its hydrophobicity, actually. And then there's some really exciting biological based coatings that are coming online right now as well. So it's really kind of looking at a multidisciplinary approach to how we can achieve that. But even things simple as like rice hulls, adding in things like that can help decrease the hydrophobicity. There are some other avenues that we're exploring. As I mentioned, when fungi are alive, they can become hydrophobic or hydrophilic depending on what the organism needs at the time. When it becomes hydrophobic, it's alive and well, and it's full of water, and it's happy and doing its thing. But when it needs to rest because it's realizing that conditions aren't right, it'll dry itself out a little bit, and that's when it becomes hydrophilic, so that when conditions improve, it can absorb that water again and continue to grow. But what we found is that when we, at the end of the growth process, and we finish that drying process, that amphipathic pathway is what it's called, where it can switch to both sides, is now cut off because the organism is no longer alive. And what we found is that if we then re-soak the material and then dry it out again, and then we can actually do that another couple times, each time we do that, we reduce the hydrophilicity that is common with most mycelium-based composites. As well, straight out the box, though, our numbers for that 2-hour submersion test were about 10 times lower than the published data, and I think that's because of the incredible density of the hyphal mat that we're growing in our parts, and so there's much more surface area of fungus throughout our parts as opposed to the biomass that's in there from the discrete particles, in our case hemp hurd. And hemp is very absorbent, but when we coat it with fully coat it with the fungal mycelium, it lends itself to help stave off that hydrophilicity. So those are some of the avenues we're looking at.
Great, thank you. We have a lot of questions in the chat. Please feel free to unmute in the order, and yeah. Otherwise, I'm
gonna
happy
call you out, Arthur. You're the first question.
Thanks, Mama. I think it was actually kind of addressed by Joshua just now with just the different methods that Okom is approaching for keeping off decomposition. So I'll refrain from my thanks.
Yeah, just to add on to that, because decomposition is an issue too. What's interesting is if you were to just pop this part into a compost pile, it would, it's backyard compostable, in about 90 days or so. But if it's protected protected in a wall cavity, for instance, or used in an interior partition or something like that, just like, wood decomposes as well, so when we use lumber in the built environment, we have to protect it in various ways. And so a lot of the same building science would apply to using mycelium-based composites in any exterior facing fashion, like load-bearing walls.
Josh, I've been reading through the questions and I've decided to summarize them for you.
Sure.
So the first one is, how do we contrast ourselves from ecovative? The second one, there's a gentleman, Lucas Johnson, is looking at replacing concrete in his foundation. Is that feasible right now? And finally, Ismail, he has a school, it's a private school for children, and is wondering how scalable we are right now. He wants to incorporate mycelium in his ceiling panels. So you can maybe talk about it. Yeah. Sure.
Yeah, our material just incorporates just a completely different methodology from what was previously known about creating mycelium-based composites. We can get into some pretty esoteric aspects of patent law at that point, which we don't need to get into here. What was the second one again, John?
Replacing foundations with mycelium.
Yeah, so that's quite interesting. So one of the things that we're looking at is, as you saw in the stress strain curves, the material is quite ductile. And John pointed this out to me early on, that when we got our first stress strain curves, he said, boy, the morphology of these stress strain curves looks a lot like steel. Now, let's be very clear here. We are not at all saying that it's strong like steel. The steel is like up here and mycelium-based composites are way down here. But the morphology, the ductility of the material, the morphology of the stress strain curve shows us that ductility can be used, for instance, as a replacement for rebar in concrete slabs or concrete columns. And interestingly, because of the nature of our material needing to have a larger form factor, we can actually displace a lot of the concrete needed to create a slab or a column. We've made some concrete columns that are solid concrete, and then we've made some with one of our cylinders in the middle. And then that initial anecdotal evidence just showed that we were able to displace about 25% of the concrete mass, and that we think we can actually get better using geometry in very interesting ways. That's John's actually expertise. I hope I'm answering that right, John.
Yeah, you are. Also, I think one thing we can add, we're also looking into making insulated concrete forms. So if you're looking at the foundations, rather than using your old school forms, we could use the mycelium as the form, and then you pour the concrete in between. Right. That's one other way to work with you on the foundation. And maybe
and it's
go ahead.
Yeah, and it's neat because then you're adding some insulation in there as well, and then again we just still needs to be tested, but we're again reducing the amount of concrete. Any reduction in concrete is a reduction in the embodied carbon impact of concrete, and then also it's making a slab or a column much lighter. So we're moving towards that lightweight structure that is the architecture of the future. And then the last question about scalability is an interesting one. We understand that we can kind of get over our skis, and the thing that can kill a startup really quickly is trying to scale too quickly. And then hearkening back to Dr. Elsacker's admonition that, you know, we shouldn't be developing products until we really understand the material really well. And so that's why this partnership with Argonne National Lab is going to be so beneficial for us, is that we're going to be able to further the material science side of it a lot farther, all while also utilizing their prowess in developing commercialization strategies to get there. So we're not quite there yet to do really any large scale projects to create, you know, wall sections, you know, much bigger than like 4 by 4 foot wall sections that are 8 inches thick, for instance. So we're still at quite a small scale, but we are developing some tools that are helping us create larger sections. It feels like I've been saying we're 18 months away for the last 18 years, but we've only been at it for 5 years, although it feels like 18 years. And so I feel like, though, at this point, especially with this partnership, that we are about 18 to 24 months from being able to produce this at a scale that would allow us to do some more demos in the wild.
That was a two-part question, Joshua. Thank you for sharing that information. The other one, it was,
Sure.
and I guess it's in parallel to what you just said, right, about doing a lot more research, because I have a school with high acuity intellectual and developmental disability for kindergarten to 20 years old. So if we apply it as a sieving panel, do you think there's going to be some concerns for allergens and things of that matter? And, you know, that's why I wanted to see the scalability, and if there's some concerns.
Yeah.
Respiratory or allergy.
Yeah. It's a very good question. And right now, the textile reinforcement phase we're using is an organic cotton. We're using hemp hurd as the main dispersion phase. And then the fungal mycelium, the fungus that we use is in the polypore family in the Ganoderma clade, largely known to be non-allergenic. And so, you know, we don't quite know. Of course, these are some of the tests that we really need to confirm before we can put these products on the market. But from what the common knowledge is, no, none of these would cause any issues with that. We kill the fungus at the end, so it's not going to continue. It's not going to create spores, for instance, or continue to do its fungal thing that it does. You know, it's not going to create athlete's foot if you have it on the floor or anything like that. No, not like that.
Is anybody else off mute? So I have a question for you. If you're using mycelium to create the forms that the concrete's going in, are you still then using the soft form factor to create the growth of the mycelium? I lost me. I was like, ooh, I lost a step in there.
Yeah, well, that's the neat thing, is that we can create them in lots of different you know, shapes. I mean, we can curve them and bend them when they're first being formed. That's what we call it, zero form, because zero embodied carbon, it can form it into anything. So if an architect wants to do something curvilinear with some concrete formworks, then we can provide something like that, and we can probably more better suited for prefabricated sections, but yes, concrete formworks that could stay indwelling basically would be the key there. Creating lattice structures, for instance, that you could form concrete inside of. So we would start with growing the parts first in the formwork shape, and then adding the concrete later, not doing it at the same time. I don't know if that helps clarify.
Yeah, that totally makes sense. I was like, somehow you were losing me on the thing. It was just, I wasn't thinking about fabrication somehow.
Sure, yeah.
And I'll just kick in because there's a question from Evan Smith, sort of more related to the embodied carbon and the environmental impact. And so I just wanted to address that one to Evan. You know, clearly things, you know, like the cotton fabric definitely do have, like every material has an embodied carbon impact. We're obviously, because our focus is on low embodied carbon, going to be sourcing all of the materials that go into this in the best way possible for that. You know, as I was saying in my earlier part about all the different glues that get used, the amount of energy that it takes to make this is really minimal to the extreme from anything else that I've seen. The growing of the organism takes place at room temperature. The drying process requires very minimal amounts of heat, and so we haven't done an LCA yet, but having looked at the LCA of just about every other product that's out there, I think that this is going to come in on the extreme low end for actual emissions that happen when we make the product, and that the amount of carbon that we're storing in the product from the ag wastes is going to outweigh the operational emissions. So we'll be at least sort of zero net embodied carbon, but I'm guessing from sort of comparisons to other materials that will be net carbon storing in the end.
Yeah, there is a paper, and I can't recall the author or the title off the top of my head, but there have been a few attempts at some analyses at LCAs for mycelium-based composites, and they do show that they are net carbon storing at the end. And the great thing about using low energy for basically all of the aspects of this is that you can run these on renewables. And so one of the things that was really important for me is that we would kind of eliminate that potential for it to only be used in like luxury settings. And we want this to be ubiquitous and be able to be done in very remote rural settings with very little needs for power to keep things going. And so we can fully see being able to use renewables in just about every aspect of the manufacturing process.
Great. We have like 2 minutes left. So a bunch of people keep putting it in the, this is a shy group. Come off mute, ask your question. Again, both Josh and John's emails are in the chat. So if you didn't catch that, we can send that afterwards to everybody who's attending. But please come off mute for somebody to ask more questions. Otherwise, I don't know, anybody who knows me knows I will have 27 million questions. So I want to open it. John, thank you for coming off mute. Do you have a question?
Yeah, hi everyone. So my question was around manufacturing, and do you foresee this would be capable of being manufactured on site, like a pop-up factory, as opposed to having to be made off site, and then obviously all the transport carbon related issues that flow from that?
Yeah, certainly. I think that I think the future of building materials, especially if we're going to go in this biogenic direction, it has to be very regional. Every 100 or so miles, we need to have more of these factories up and running. So that means smaller footprints, but that makes it also more resilient. So I don't consider us, being some global manufacturer and shipping these things all over the world. So that distribution is quite important. And we also want to license this technology. We don't want to grow it ourselves. We want to make sure that anybody that wants to manufacture this can. But it is interesting, though. Something that is not hard to fathom is to be able to, for instance, show up with a few 40-foot containers, and within those 40-foot containers, you can do some on-site work quite easily. That is not outside of the realm of possibility. My first shop was my garage, and it did very well. So I think we can do these in very small footprints on-site. And it would have to stay there for maybe a couple weeks or so. But if the project's going to last that long, then so be it.
Thank you.
Well, thank you so much. This has been such an interesting presentation. I hope everyone enjoyed it and will want to hear more. I just put their website also, which anybody could Google in the chat. And I think there was one question, Lucas made a recommendation. Is there a listserv or something where you do regular updates of what's happening, or, what's the process to be updated?
Sure. Yeah, LinkedIn, following us on LinkedIn is a really good way. Definitely all three of us are really active, including April, really active on LinkedIn. But if you go to our website, you can sign up to our mailing list, and we send out, we will not spam your mailbox. I send out only updates as they are relevant to development. So going to our website and signing up for our mailing list is great. Write me an email. I mean, we're small. We don't think too highly of ourselves, and I answer all of my emails and love to interact with people and even do Zoom calls with folks. If you're in Chicago, write me an email, come by the lab. I'd love to show you what we're doing here.
Well, thank you so much, Chris, Josh, and Joshua, and John. This has really been a great presentation. And I have a couple minutes. I don't know if you do. I know there's, you know, a lot of people have a hard stop at 9. So unless anybody else has questions, we can shut it off. Or if somebody has a question and you guys have time, we can kind of have a.
Yeah, I'm happy to stay and answer more questions. That's great.
I had a quick question. Can you hear me?
Sure.
Yeah, go for it, Jen.
Yes, Ginger.
Yeah, so I was curious about if your preferred fungi are parasitic, and if so, do you have a way to prevent them from getting out into the environment?
Yeah. So the species that we use are in the Ganoderma family, and they are, you know, they are pathogens of trees. However, they're also widely spread throughout the world. Ganoderma lucidum is commonly used, and that is native to Asia and Northern Europe. In North America, we have a very similar species called Ganoderma cecily. Cat's named Cecily, actually, after that fungus. And so it really is a matter of choosing regionally appropriate fungi. But we do know that certain fungi have better abilities to produce these. And it is using lab spaces, like for instance, we use a clean room like the one that I'm in right now to help mitigate that until we know further about that. But it doesn't seem very likely. Well, and then also I should say, people go, oh, you're the mushroom guy. It's like, no, I don't grow mushrooms. I grow mycelium, and mycelium do not produce spores. So there's really very little chance of it escaping the lab because it's not going to that sporulation. When these types of fungi do sporulate, they produce 35 billion spores per day, you know, and they produce trillions throughout their sporulation season. So yes, that would be problematic, but we're not growing those fruiting body structures that would create that sporulation. So it would be very difficult for them to escape the lab.
Cool, thanks.
If not impossible. Yeah, that's a great question, by the way.
Joshua, you mentioned you kill it so that it doesn't continue to grow. How do you do that?
Yeah, heat and basically dehydration. You dry it out and you heat it. The common knowledge is anywhere from 70 to 90 degrees Celsius. However, that may need to tick up to about 100 degrees Celsius. And again, we're just now reaching the boiling temperature of water. So it's not like it's, you know, we're not creating kilns to do this. It's just we have to heat it up enough to kill all the structures. Another interesting method that could be used is things like ultrasound and microwave technology to denature the cells so that they just simply cannot survive. And there could be some benefit to repolymerization using those technologies as well.
Okay. Seems like we're getting to the end. Excellent. Well, again, thank you so much. Super fascinating presentation. Really excited to see where this technology goes. And thank you again. And thank you, Autodesk Research, for having this opportunity for Okom Wrks to speak.
Thank you so much. This has been a really great opportunity, and I'm very thankful for the opportunity. Thanks a lot, Rama and G.
Bye, everyone.
Ciao for now.